Okay, it's really a pleasure to be here today. Very exciting conference, a lot of great things, a lot of discussions. So I would like basically to introduce this talk. It's going to be about learning Agile vision-based flight, and I want to tell you basically the most recent results over the past 1 or 2 years. And I know that the focus of this workshop is about reinforcement learning, but actually I'm going to talk a lot also about imitation learning, and then also how we can start leveraging deep reinforcement learning. But what I'm going to present today wouldn't be possible without the great help of my students, and the work I'm going to present today is actually due to the students who are listed here: Ilya Kaufman, Antonio Guercio, Leonard Bauersfeld, and Yu Long Song. Before I start, I would like to ask you, how many of you will work on vision-based navigation? Raise your hand. Okay, very good. So drones are very, very difficult to control because they are very unstable and they need constantly a position information coming from their onboard sensors. So most of the commercial drones that you read in the news every day, actually I would say 99%, are actually not flying really autonomously, they're flying with GPS. So what is autonomous is not the drone, it's the constellation of satellites around the planet plus the drone itself. Now, if you want really drones to be deployed in the real world and even search survivors in the aftermath of a disaster, they will have to rely on onboard sensors. But you cannot put a LiDAR on a drone because it would be too heavy. So 13 years ago, I started working on vision-based navigation. What you see in this video is what we believe is the first demonstration of an autonomous drone relying on an onboard camera for vision-based navigation. It's using SLAM, visual SLAM, running in real time, and the map was not a priori known. Actually, the drone is creating the map in real time. At the time, we were using PTAM, that had just been released at the time. What you also observe is that one of my students at the time is securing the drone with efficient roads because the regulations of the university didn't allow us to actually fly drones freely. And also what you probably observe is that there is a very long USB cable. So we didn't have enough computing power to do all the computation on board. So we actually relied on an off-board computation. So we had a 20-meter long USB cable connecting the camera to a laptop sitting on the ground. And then we participated in the European micro-aerial vehicle competition, and that consisted in going from A to B and passing even through a narrow gap, like a window. Where do we stand today? Well, today we have now vision-based drones flying autonomously on Mars. As you know, Mars is not GPS. And this is actually flight number 4 from April 2021. And we also have Skydio drones or DJI drones that are actually being used more and more for autonomous or semi-autonomous inspection of difficult infrastructures like buildings, like bridges, power masts, and so on. And they use actually only onboard cameras and computation. And what I would like to stress is that the vision is really more important for flying robots than ground robots, because on ground robots actually you have enough payload to actually put LiDARs and very power-hungry GPUs. But on drones, actually, you have severe power constraints, size constraints, and payload constraints. So we have seen a lot of things in this conference, and sometimes I try to ask myself, where are we going as a community? What is that we want to achieve as a community in robotics? And we have seen the great demonstrations by the lab of Marco Kutter, basically that showed that ground robots are getting very, very agile. So basically it seems that we, as humans, are trying to make robots as good as us, or even more agile than us. Because if you want robots to possibly help humans at repetitive tasks, they will have to be more efficient than humans, not just, accurate. And so where are we going in terms of drone navigation? I believe that what we really should strive for is to try to make drones as good or even better than human pilots. So if you look at autonomous drones today, look at the previous videos, the Scaramuzza drone, or for example, the NASA drone, they are very, very clumsy. So the performance of autonomous drones is still very far away in terms of speed, versatility, and robustness from what human pilots are capable of doing. Look at that. They can actually deal with motion blur, very limited field of view, and the huge delay involved in the processing by the brain. Of course, you may ask about why do we care? Well, first of all, because we care about flying agile, because if you want robots to be helpful, they will have to be faster than humans, more efficient than humans. But it also matters because at the moment, drones can only fly for 20, 30 minutes. And what we found out is that if they fly any faster, they can actually be more useful. They can accomplish more in the limited amount of time. This was a paper that Leonard published at this conference. So by flying faster, drones can increase their range. But also, by flying more agile, actually, we can serve many applications that range from search and rescue, delivery, exploration, personal flying cars soon, and the next space missions that were outlined in the NASA talk this conference. But also, flying agile raises a lot of interesting challenges for perception, learning, planning, and control. And especially it allows us as a community to push the limits of vision-based navigation. But in order to understand how we can make autonomous drones as good or better than human pilots, we first need to understand how human pilots control drones. How do they control drones? Well, vision-based, actually. So we actually started studying human pilots. We invited 20 human pilots to our lab, and we installed eye trackers on their eyes while they were doing drone racing tasks on the famous drone racing simulator, which is actually used to recruit professional drone pilots for real-world competitions. And what did we find out? Well, we recorded their eye gaze, control commands, and what we found out is that actually there is a delay of about 220 milliseconds that contains both the brain processing latency and the behavior response. How does that compare with car drivers or car racing? Actually, in car driving, the latency will be 185 milliseconds. So we tried to understand why is it actually a higher latency for drone racing, and what we speculate is because the task is much more difficult, because you have to fly in 3 dimensions, so you have to reason in a larger amount of hyperparameters. But 220 milliseconds is quite a lot, if you think about. I mean, our algorithms run at 20 milliseconds latency. So how come that still human expert pilots are better than any drone autonomous pilot? And the reason is because, yes, the human brain is incredibly slow, but it's much better than machines in making decisions in complex situations. But now let's move to the technical stuff. We want to do autonomous vision-based agile flight. So I would like to introduce you our drone. This drone is about 20 centimeters in size. It has a brain, an NVIDIA Jetson TX2, and then we have eyes. We usually put stereo cameras or single cameras, and we've been using a lot of inter-real sense devices. Now, how do you control a drone? Well, traditionally, you control drones like any other ground vehicles, like autonomous cars or electric robots. So basically, you have this traditional control architecture that consists of a cascade of different modules, a module for perception that basically does, for example, state estimation and mapping, a module for planning, and a module for control. This architecture has worked for almost 40 years. So there is nothing wrong. But there are some limitations. First of all, what we observe, as you all know, is that it is very sensitive to inaccurate models of sensors, of the actuators, of the environment, battery voltage, aerodynamic effects. It is also very sensitive to imperfect perception. Think of motion blur when you especially fly very fast. Also the limited field of view that basically causes feature tracks to be suddenly lost completely. Also, what it does is that this architecture ignores the fact that perception induction, especially for drones, is strongly coupled. Why? Because drones need to observe constantly features in order to reliably just hover. Imagine if you just want to hover on here, you need to look at some stable points. But if there are no points, the drone will crash. So now when you want the drone to actually to follow any maneuver, you have to ensure that there is enough features and that these features are constantly visible. What if there is only one feature in the environment then? Then in this case, you would have to make sure that you always look at the same feature. So you have to basically kind of solve a chicken and egg problem. You have to look at the features without which you won't be able to localize. Another problem with this architecture is that, you know, this cascade architecture actually provides a compound latency that can really negatively affect the overall agility of the platform. As you can perceive, the agility of the platform depends on the total latency. So the larger the latency, the slower you will actually navigate. So, and what would be the extreme architecture? What would lay on the other extreme of this architecture? Well, the other extreme would be to basically learn a policy that maps directly sensory inputs to control commands. And we have seen immense progress in this for several tasks, like for manipulations, for example. But the key issues are, as you know very well, is that it's too sample inefficient to be trained on physical drones. Because how do you collect all the data? You will have to crash a lot of drones, so we need tens of millions and also a lot of engineers to repair all the drones. You know, I show you later a lot of spectacular crashes. It's very difficult to research on drones. And also, such an architecture actually lacks interpretability. So the key question that I want to answer in this talk is how can we augment the traditional robotic control architecture with learning-based methods? And the key questions that I'm going to answer are, should we train it with or without supervision? And how do we get enough training data? Can we learn it in simulation? And how do we address the simulation to reality gap? But now, I don't want to talk abstractly. I'm going to talk specifically for some tasks. So I'm going to focus on the tasks of autonomous acrobatic maneuvers, navigation in the wild, that means in unknown environments like forests, and then autonomous drone racing. So this is a paper that we presented at RSS 2 years ago, where we showed for the first time an autonomous drone using a single onboard camera, an inertial sensor, and an onboard Jetson computer to perform agile acrobatic maneuvers that are similar in agility and accelerations to those performed by human pilots. You can already tell the difference between this one and human pilots. What is running here is a neural control policy that was learned actually only entirely in simulation. This is actually what the simulation looks like. We simulated hundreds of drones performing different acrobatic maneuvers. And this was the equivalent of 50 flight hours, and it was possible actually in just a bunch of hours overnight. What did the simulator look like? Actually, the simulator that we used 2 years ago was very basic. It was our first attempt to actually solve this problem, so we didn't really want to invest much time in the photorealism and so on. And actually, we used gazebo, which is on the left. But then we wanted to make sure that the drone would then fly in the real world. And ideally, one single shot simple transfer without any fine-tuning. How is this possible? As you can see, the simulation and the real world look completely different. So how do we address the simulation to reality gap? So there have been interesting works that are studied there below, where basically they have shown that one way to actually address the simulation to reality gap is to find appropriate sensory abstractions. So basically to convert the input images into something in the representation that then you feed to the neural network. And I like particularly this paper by the group of Vlad and Colton at Intel, where basically they show the neural networks fed with intermediate representations that train faster, achieve a higher task performance, and generalize better to previously unseen environments. So what would be an appropriate sensory abstraction for the task of drone acrobatics that would transfer from that simulated world to the real world? Actually, is Fisher tracks. As you can see, and Fisher tracks actually look similar in the simulated world and the real world. They don't depend on the type of texture in the environment. So it doesn't matter whether it's really photorealistic, Hollywood style photorealism or not. So that's why we managed to actually use gazebo with such a crappy photorealism. In addition, what we also showed in the paper is that with the sensory abstraction, we also reduce the fastest time distance between the observation models in simulation and reality. Now, how do we train this neural controller? We use the privileged imitation learning. So in imitation learning, what you're trying to do is to basically imitate an artificial expert. actually let's say more generally, you're trying to imitate an expert. And you're trying to distill the knowledge of the expert into a neural network. For us, the neural network that we actually used as an architecture was a temporal CNN. But now, do you want to imitate humans? No, because ideally you want to be better than humans. So actually for us, the expert was an artificial expert. And what would be the best artificial expert for drones? Nonlinear model control, NMDC. But now this expert is privileged because it has access to privileged information like Oracle, God information. So it knows perfectly the state of the drone and perfectly the environment. Of course, this information is only available in simulation. And so we basically generate all the trajectories that we would like, to teach the control policy to imitate. Then the NMPC generates control commands for specific trajectories. And then our neural network tries to imitate those control commands. Now the input to the network, then when you train it in simulation, will be official tracks, IMU, and of course also the reference trajectory that you would like to follow. And we've seen that it works. But now let's try to quantify. Okay, qualitatively it works, but how better is it than a traditional model-based control architecture consisting of the estimation, planning, and control? So we compared against a traditional architecture consisting of a vision immersion volumetry plus model-ability control. And what we found out is that the learned end-to-end control policy outperformed the traditional architecture by 25%. On the left, you see actually the trajectory tracking error. So we are better than the VIO plus MPC, and we are also better in terms of success rate. Actually, over maneuver time, so up to 20 seconds, we had a success rate of 100%, while the VIO plus MPC only a success rate of 90%. So it would actually crash 2 times out of 20, which is actually pretty bad if you think about it. We don't want our drones to crash on our heads. Now let me move on to another difficult task. And the task I'm going to talk about is called navigation in the wild. What is the wild? Let's have a look. In the wild, the robotic means navigating in unknown environments, for example, a forest. Here you see our drone navigating both in the snow and now in different forests around our lab. Here in the firefighter training arena of Zurich. Here in a hangar. And the one following is Scaramuzza. This one is again ours, first-person view video. Notice how agile and how abrupt are the roll angle, because it has to make decision very fast, and in the end the quickness of the reaction time it depends on the sensing range. So this paper was published as Robotics, and we released fully the code. Now, how did we train this? So we didn't go outside and collect data in the real world. First of all, it would be illegal in Switzerland. It would also be very tedious. It would take months or probably years. And it would be very, very difficult to repair the drones because you're going to crash hundreds of times. So again, as before, we collect data in simulation. But now, as you can see, the simulator is a bit more sophisticated. So here, actually, we benefited from the fact that there is now a lot of video games with beautiful sceneries. So we downloaded a lot of forest-like environments for Unreal Engine. And then we imported it in our drone simulator that we released 3 years ago, which is called Flightmare. It is compatible with Bullet, with ROS, and other things, and the gazebo. And so in simulation, what we do is that now we have again the artificial expert that knows perfectly the forest and knows perfectly exactly the position, orientation of all the trees, their diameter, everything. He knows everything in advance. And so using the simulation, our expert generates a global trajectory that takes the drone safely through all the trees until the end of the forest. Here, the goal was to fly straight, avoiding trees, of course. However, do you think that would be enough to imitate just, a single global trajectory in a receding horizon? No, it wouldn't be enough because in reality, what if you have, for example, a double slits? Do you go left or right? So the real world is full of ambiguities. So we need to have a policy that is able to actually cope with ambiguities. So we are not imitating actually the global trajectory in a receding horizon fashion. What we're actually imitating is a multimodal distribution. So at training time, the artificial experts also generate Monte Carlo samples. of collision-free trajectories towards the direction of the global trajectory. And then the artificial expert tries to imitate this distribution. More details coming in a few slides. And then now let's go back to the question before. How do we cope now the sim to real transfer? So look at on top what the simulation looks like if you render images, and the real world, what it looks like. They're still pretty different, aren't they? So which sensor abstraction here would reduce the sim to real gap? Well, what we found out is that depth maps reduce very well the sim to real gap because they are independent of the texture. So it doesn't matter what color you paint your trees, yellow, red, or whatever the season of the year, and so on. The depth maps will always look the same. Actually, though, there is something more, because now when you generate these depth maps in simulation, you could actually generate them from ground truth. But that's not what we did. Actually, we generate left and right stereo pairs, and then we run a semi-global matching to generate the depth maps. Why do we do that? This is very important. This is very important because we want to generate a realistic, noisy sense of data. So semi-global matching really is the key algorithm used in computer vision to match left and right stereo images. And you can notice that we are doing this because you see that all the three trunks have these white edges. What are they? They are the typical occlusion artifacts that you only have when you basically do left and right stereo matching. Otherwise, they wouldn't be there. And also, you are actually simulating now realistic noise. This is very realistic. In the paper, we ablate with respect to without, this noise observation and with noise observation, and actually observe that there is a huge, significant performance increase when you actually train on these noise observations. Now let's go back to how we train it. Also here, as you understood, we train it with privileged imitation learning. So now what is the expert? The expert is a Monte Carlo sampling algorithm that generates basically a bunch of thousands of collision-free trajectories, but it's quite too many to imitate, isn't it? So actually we're not imitating these thousands of trajectories. We're actually we're using the k-means algorithm to select the 3 best trajectories. And then we try to imitate those 3. And each trajectory is parameterized in terms of waypoints. Actually, 10 waypoints for each trajectory in a receding horizon fashion, 1 second ahead. So we have basically 30 points. And then, now this is interesting. So we don't go directly to control commands, but then out of these 3 trajectories that are output then by the neural policy, what we do is that we select the one that actually is best to be executed because they are all safe. But then you also want to make sure that this trajectory output by the network is continuous with respect to the previous executed trajectory. So we use this continuity constraint to actually select the optimal trajectory. And also we also have a kind of a score that we want to minimize. Then we basically output a single trajectory that then we execute using non-linear model-predictive control. So basically there is this abstraction layer also for the output commands. And now let's go to the results. How does it compare to the traditional model-based control architecture of state estimation, mapping, planning, and control? And the results are quite surprising. So first of all, who are our model-based baselines? We took 2 of the best for which there is code available. We took the one from the group of George Shen at Hong Kong University of Science and Technology, and we took the one from Russell Drake. So the one brought by Shen is actually doing incremental mapping and receding horizon planning, while the one by Drake, which we call reactive, actually does purely reactive navigation. So there is no receding horizon planning. And what we observe is that the fast planner, since it uses much more information, it does mapping, then it computes a lot of trajectories, and it does collision checks. It's actually pretty slow. It takes 65 milliseconds for each depth map. While the reactive one, of course, doesn't have to reason in the future. It's actually much faster, 20 milliseconds. While ours actually takes 10 milliseconds. So it's twice as fast as the reactive one and 6 times as faster as the fast planner. But now let's look at the success rate, where 100% corresponds to basically going to the end of the forest without ever colliding with the tree. But we do this, we compute the success rate over different speeds. So we are interested to basically fly as fast as possible safely. So we can see that with the neural control policy, so ours, we can actually fly up to 10 meters per second, which is almost 40 kilometers per hour, with a performance, with a success rate dropping only to 60%, which is actually not bad. So 60% of the times we'll be able to not collide. While instead, if you look at the other two baselines, actually the performance drops significantly at half of the speed. What about sensor noise? How do the traditional baselines handle noise? Well, it's actually quite surprising. Fast Planner, for example, if you run it with and without noise, with noise, the performance drops by 100% at 5 meters per second. While at those speeds, with our neural control policy, the performance only drops by almost 5%. And let me show you additional videos. So this is another video that we recorded. So this is being deployed. There is no fine tuning here. We never do fine tuning in these works, neither drone robotics, neither here. So the drone had never seen these environments. Okay, it only saw trees in simulation. This one is also very interesting in a little bit of low light in a fog environment. Why is this possible? Is it possible because remember, we are not using raw image pixels, but we are actually training on depth maps. So this sensory abstraction transfer better from simulation to the reality, and also among different real-world environments. So what are the takeaways? The takeaways are that basically what we found out is that complex navigation strategies can be distilled into efficient deep sensory model policies. Also, what we found out is that learning-based policies are more robust against sensing noise and at lower latency. Also, what we found out is that abstraction of policy inputs enables robust transfer from simulation to reality. Now, the problem is that we are still relying on all this data. Another question is, what if there was a task where no labeled expert data existed? Then we cannot create such an expert. Is there such a task? Yes. It is the task of drone racing. Drone racing is very, very important. It's very, very difficult because every little mistake can lead to crashes. And in drone racing, humans are really pushing the drones at their limits. And then there is no model-based algorithm at the moment that can actually, get as close as humans unless you use estimation from motion capture. Let me show you our human pilots that we are trying to beat. His name is Marvin, and Marvin is 15 years old.
Get ready.
So we invite Marvin often to come to our lab, and now let me show you how he is. Marvin is flying here about 72 kilometers per hour. You know it was remembered. Thanks to maneuver, normal the motion blur, and so on. These beautiful images, by the way, are coming from the book. Because the images that human pilots see are actually from analog cameras, and so they're pretty bad. But drone racing is super difficult because, as I was telling you, the drones are constantly pushed to the physical limits. So you're really working at the, at the boundaries of what each model can possibly achieve. And any small mistake can lead to a crash. Look at that. Each of those costs about half an hour or 1 hour of repair. So now I'm telling you this because it's difficult to deploy this and do like online learning. You understand? You cannot do that. You can do this on a ground robot, like a wheeled robot or a legged robot, but on drones, you cannot do it. You cannot afford it, unless you have tons of money and tons of engineers. So let's try to investigate mathematically what the drone racing problem is about. In drone racing, the problem is to find the control inputs u as a function of time that minimize the flight time to pass through a series of gates from the start to the finish. So you want to minimize that integral subject to system dynamics, input constraints, state constraints, and physical constraints. So last year, Yu Long, my PhD student, started working on reinforcement learning, deep reinforcement learning for autonomous drone race. And here I show you very quickly some results. So here is actually the network that we're using is a simple MLP, multi-layer perceptor with just 2 layers that takes us input position, velocity, orientation, body rates, and gate observations, and outputs then commands. I'll tell you later what the right commands are for doing these agile maneuvers. Then we use a PPO. We do parallel sampling of 100 quad orders. We use a distributed initialization strategy. We use 500 seconds of flight time per update step. And then the typical training requires about 1,400 hours of flight time or 2 to 3 hours of work clock time. So actually you can do it in just 3 hours. And here you see actually the training happening and how the policy actually learns and improves over time through all the steps. Now what I'm going to show you is training results that now we are doing in onboard vision-based. So quite new. This is vision-based. There is no motion capture, not this yet. Not to look at the onboard unit and the gate detection. Here the drone was flying at 70 km/h. They are very close, Martin. We hope to beat him soon. This is what the images look like. Look how motion blur they are, especially when there is a sudden change in orientation of the drone. That actually usually happens when you have to make a very sharp turn. And also observe how, because of motion blur and high-speed rotational motion, suddenly, the feature tracks, the gate corners disappear and then reappear. So this is the problem with vision, you see? And if you lose that, then you crash. So that means you actually have to couple perception and action. You always have to make sure that you always look at the next gate. So that's what we're working on. And there is a problem. How can you train such an agent to then perform in the real world? I mean, there will always be a mismatch, a physical mismatch, especially, like real world aerodynamic effects. So we're working on improving simulation, improving the physics of our simulators by collecting data in the real world and then going back in simulation to improve our simulator and then going and deploy in the real world. So we published a paper at RSS about basically modeling aerodynamic effects. Look at this. The drone was performing at sharp turns and you generate a lot of turbulent flow. You cannot model that unless you use, computational fluid dynamics simulators that take hours, and you cannot do this for every maneuver. It's, just not impractical. So our idea in this paper, and we also published a code in the data certificate industry, is to actually use a combination of first principle models from physics, like blade element momentum theory, where we model all the wind profile, the bending of the blades, and so on. And now we learn residual models of forces and torques that cannot be explained by first principle models by collecting data in the real world. So in the real world, we have a beautiful motion capture. We fly trajectory super fast from 0 meters per second to 20 meters per second, so 70 kilometers per hour. And then we look at the gap, discrepancy between the executed maneuvers and the desired maneuvers. And then we use this gap to actually train these residual models. And what we observe is that by using these learned residual models, we can improve the physics realism with respect to classic drone simulators for agile flight by up to 60%. So I invite you to have a look at the paper. And this leads me to the conclusions. So in the end, what I would like to point out, so deep sensory model policies allow us to push robotic platforms to their physical limits, even with onboard sensing and computation. It is possible. Simulation to reality transfer can be facilitated using abstraction of policy inputs, like I told you, official tracks of depth images, but depending really on the specific task that you're tackling. But also what we observe, and this one I didn't talk about, also what is important to reduce the synthetic gap is the appropriate choice of control modality. What we found out, and Elia presented this yesterday, is that collective thrust and body rates achieve a high agility while being more robust to domain shift. So we have also compared it to velocity commands and single roll thrust, and we found that collective thrust and body rate have actually much better performance. And also what I show you is that by improving simulation of aerodynamic effects, allows basically to reduce the synthetic gap. And with this, I would like to thank you for your attention.
Thanks a lot, Davide. We have time for a few questions from the audience. Please come up to the microphone.
Hi, thank you for a really interesting talk. I was wondering, so you mentioned, this and reiterated in the conclusion, talking about choosing the right feature description or the right modality or the right abstraction for the inputs to the network. Do you have sort of guidance and generalization of that? So what to look for in choosing that?
Yeah, at the moment, actually, what we did is that we followed our intuition. So, of course, there are papers that try to actually learn such a representation, but they were never been tested on such difficult policies. So, at the moment, we chose it.
Okay, thank you.
Thanks for the talk. That was yeah, very interesting. I guess I have one curiosity when you were talking about your flight in the wilderness and that sort of thing. So you sort of judge your performance on whether you collided with a tree or an object in one of your runs. But I guess based with all the sort of work that you've been doing, is it possible to train a drone to recover from a collision?
Whoa. Generally, no. You can't recover from it. It depends on the impact, obviously. I mean, if you look at the works done by Professor Dario Floriano at PFL, he has done a beautiful line of works on resilient drones that are actually made of soft materials that actually, yes, they can recover, and then they have meshed the drones, you know, at incredible speeds against walls and ground. So it is possible. Unfortunately, the drones we're using actually have rigid parts. So really, when they impact the walls or the ground at those speeds, they actually break blades or an arm and so on. So we would rather try to avoid crashing, but you can't avoid it that much in drone racing, okay? Because there, every little mistake can, and even every bunch of milliseconds difference actually matters, can cause a crash.
Thank you.
Hi, I have a question regarding the action representations that you mentioned that you have to choose well to learn. So you mentioned at the beginning that if you have to do any perception, we have to get background models, accuracies, and latencies. But for example, in the flying with the forest part, you also use the model with control in the end that in the end also needs estimated onboard information. So I wonder, how do you deal with this trade-off of still having to use some traditional perception for the local controllers to be able to learn higher level actions, but still not run into these problems that you mentioned earlier?
That's right. So, okay, wait. Let me differentiate. So, for the task of deep neural robotics, basically the network's observation are the feature tracks, the altitude, and the reference trajectory. Instead, for the task of navigation in the wild, we input the depth maps, also visual odometry estimates, so basically the poses. So yes, that's correct. So at the moment, we are not actually able to go, if you want, from just pure depth maps to the output. So we need this additional information. That doesn't mean that it's not possible. We know it's possible. Animals and humans do that very well. It's just that, you know, it's just too sample inefficient at the moment, but it will certainly be done soon at some point. The point is that at the moment, we cannot also guarantee that it will generalize to other tasks. That's always a problem. How much data can you actually simulate in simulation to allow sufficient generalization to different environments? So at the moment, if we remove the state estimate for navigation in the wild, we will be able to do it.
For the latencies there, it didn't cause problems.
Okay. The latency there, no, for state estimation, it doesn't really matter. The latency of the state estimation, which is actually not a problem at all, because it's coming from visual inertial odometer at 200 Hertz. The real latency, actually, so there is two different latency here. We have the sensing latency of the inter-real sense stereo camera that has a frame rate of 15 Hertz, so 66 milliseconds. And then we have the perception latency that is actually only due to the neural network that maps directly to the trajectory. And that one takes 10 milliseconds. Yeah. Thank you.
Last question from the room.
Thanks for the great presentation and talk. So you mentioned that you are also doing research on event-based cameras, event-based input as well. So have you done any work in trying to use event-based input, because that would have given you more, I would say,
yes,
lower latency?
Absolutely. So what's the goal after we have achieved the human level of superhuman performance? Well, we want to achieve ideally the agility of birds like sparrowhawks. Look at that. And so it turns out that you cannot do this with standard cameras because you need to wait until the next frame arrives, but you can actually possibly do it with event cameras. And we've done some work on that. And one work that for which we received an award yesterday is this one. Basically, we were able to actually hover a drone subject to rotor failure thanks to the low temporal resolution of event camera. So if you use a standard camera on the left, the drone will eventually crash because of motion blur. While using an event camera, you can actually sustain flight at lower illuminations thanks to the fact that there is no motion blur and very high temporal resolution. Or you can also dodge objects thrown at the drone, here with latency of 3 milliseconds. Now, the next step we would like to investigate is now to go back again to event cameras and try to learn a control policy that map, if you want, sensory abstractions or directly raw event information to control commands. So that's what we are actually investigating now.
Awesome.
Perfect. We've got 2 questions from the Zoom audience here. I'll read it out. The first one is, does the learning-based method deteriorate drastically when faced with large sensor noise in flight?
Large sensor noise. So we have done all the tests also in simulation where we had a lot of noise, and we observed that actually it of course eventually deteriorates. So, but we simulated realistic noise. We didn't really simulate very surreal noise. But what we observe is that the performance deteriorates in low illumination. So the camera has its own built-in exposure time. We cannot control it, unfortunately. But basically what happens in low light is that the gain of the camera automatically increases and it increases the noise. And then what happens is that the depth map actually now is flickering and there is a lot of missing data. And in this case, then you start to observe also that the performance deteriorates. But in general, it deteriorates much less than with the classic architecture. So the performance drop in terms of success rate was only 5% compared to the performance drop on success rate of the traditional architecture. So it deteriorates, yes, but much less. So it seems that the neural control policy is more robust to noisy inputs of the sensors.
All right, thank you. And last question here also from online. Have you tried any onboard training to improve on the sim-to-real gap in completely unknown environments, for instance?
We are working on it for the task control racing, you can imagine. So this is, of course, what you want to do. So to basically gather data in the real world and then try to do real world adaptation. So that's what we are currently working. But you cannot afford, too much, tuning because of the crashes that you will ultimately have. And that's the point. That's the key difference with the ground robots.
All right, thank you again, Davide, for this fascinating talk.
Thank you.